Hey everyone, Dr. Tom McNamara, back again for our course in trigonometry. We are continuing our work with these inverse trig functions, and we are going to talk about applying identities when inverse trig functions are involved. Let's call it maybe identities and formulas with inverse trig functions. So let's look at this example right here. I've got an expression and I'm asked to find the exact value of this expression. Okay, remember we've got two notations for inverse trig functions. One of them is an exponent of -1 by the function name. So in other words, sine inverse of 4/5 would be an alternate way to write that. All right. So I've got arcsine of 4/5, I've got arc secant of -2. And all that is being put into the cosine function. So I'm taking the cosine of this thing. Now each of these things is an angle, right? If I take the arcsine of something, it gives me an angle that would have 4/5 as its sine. Okay, so this is an angle. This is an angle. You add two angles, you get an angle. So it makes sense to talk about taking the cosine of this expression. Couple things I want to note here. Angle sum formula for cosine. Cosine of A plus B is cosine A cosine B minus sine A, sine B. Okay, so that's the first thing I'm seeing here because I got cosine of a sum. I can apply the angle sum formula. All right, so this expression is equal to cosine of arcsine 4/5 times cosine of arc secant -2 minus sine of arcsine 4/5 times sine of arc secant of -2. Okay, it's a lot of writing. I know it looks complicated, but it's really not so bad. Okay. Let's look at this right here, cosine of arc secant. Okay, now we haven't actually talked about the arc secant function before, and if you look at your calculator, you will not find a button for the arc secant function. Okay, but remember, secant is related to cosine. Secant theta is the reciprocal of cosine theta. So arc secant is telling me an angle that would have -2 as its secant. So if I know the secant of an angle is -2, then I know the cosine of that angle. And look at what we're doing. We're taking the cosine of an angle whose secant is -2. So if we take the cosine of that angle, we're going to get -1/2. Okay, so that's what that expression is right there. Now right here, let's look at this. Arcsine of 4/5. Arcsine is an angle whose sine would be 4/5. So we're taking the sine of an angle whose sine is 4/5. We get 4/5. Okay. The only two things that are going to give me a little bit of difficulty are these two expressions, and even those aren't so bad. Let me go up top here. Arcsine 4/5. Arcsine 4/5 is an angle, theta, whose sine would be 4/5. So the opposite side is 4, hypotenuse is 5. That means the adjacent side is 3, right? It's a 3, 4, 5 right triangle. So that means I know this expression. The cosine of that angle theta, adjacent over hypotenuse, 3/5. Okay? And now I got to work on this. I know the arc secant is -2. Okay, so arc secant, -2. That must mean I have a cosine equal to -1/2, as we saw right here. Okay, so that must be putting me in my second quadrant. The only reason I'm going to the angle and standard position version is to deal with this negative. Okay. So this hypotenuse must be a 2, this must be a 1. Okay. Use the Pythagorean theorem to figure out that's a radical 3. Okay, so arc secant -2 must be talking about an angle like this. Okay, arc secant and arc cosine would have the same range. They'll always give you something between 0 and 180. So if my secant is negative, arc secant is going to give me something over here in the second quadrant, and the sine would be positive in that quadrant. And since I use my Pythagorean theorem there, right, this point has coordinates -1, radical 3. So my sine is negative radical 3/2. Okay, we're doing some work with fractions here. Not hard. To multiply them, go straight across. This is -3/10. Well, this is 4 radical 3/10. And that's a minus, so 4 radical 3/10. Okay, so we've got the exact value for this. So, a couple things to think about here. Firstly, I'm looking at cosine of a sum. Use the angle sum formula. And now I'm using the nature of inverse trig functions. Some of them you can figure out by inspection. Like if you have sine of arc sine, no need to do any work at all. If you got a situation like this where you're talking about cosine of arc sine, you're taking the cosine of the angle, but you know the sine. Make yourself a little triangle and figure out the remaining side, and then you can get the cosine. Okay, let's do one more. So we're going to find the exact value of this expression. I'm sorry. Yeah, find the exact value of sine of 2 tan inverse 3/4. Sine of 2 tan inverse of 3/4. So once again, this is going to test our knowledge of some formulas. Last time we had the angle sum formula. Here, I'm thinking we're probably going to need a double angle formula, because tan inverse is going to give us an angle, and then we're doubling that angle. So double angle formula for sine. So we'll need to have that handy. Sine 2a. Remember what that is, it's 2 sine A cosine A. And we're also going to be tested on the nature of these inverse trig functions, how these inverse trig functions work. Okay, so sine of 2 tan inverse of 3/4. That would be 2 sine of tan inverse of 3/4 times cosine of of tan inverse of 3/4. All right, so thinking about what tan inverse of 3/4 is, well, it's an angle. It's an angle theta. And what do I know about this angle? Well, I know the tangent of that angle is 3/4. So opposite over adjacent. Use the Pythagorean theorem to figure out the hypotenuse has to be length 5. All right, so we've got expressions for these things now. What's the sine of this angle? Well, the sine is opposite over hypotenuse, 3/5. What's the cosine? It's adjacent over hypotenuse, 4/5. 24 over 25. Okay. Application of my double angle formula for sine, and then knowing how trig functions and inverse trig functions work together to give me these values.